name is Dr. Esther Trufan, and in this video, we're going to explore some details about the percent yield. The percent yield is defined as the ratio of the actual yield, which is obtained by experiment, and the theoretical yield, which is calculated from the amount of limiting reactant consumed. The ratio, because of the name percent yield, will require multiplying by 100% to actually give us a percent instead of a number. This kind of problem can be applied to all manner of chemical reactions. It can be applied to decomposition reactions because this is no longer just about what is consumed, but it is also about how much of the product is actually recovered. It can also be applied to combination reaction, and here is an example of a synthesis problem where oftentimes we want to know what is the expected percent yield of a product. Combustion reactions have relatively high percent yields. Double displacements also have fairly high percent yields because of the formation of the solid that drives the reaction forward. And similarly, if we have gas formation, then often single displacement reactions can be pushed towards high completion rates. We already know the theoretical yield. We can determine it by calculation using the limiting reactant, and we are going to assume that all of the limiting reactant is fully consumed and all 100% of the product associated with that consumption is going to be recovered. That is what the theoretical means, the absolute maximum amount that one could obtain. And truly, in a chemistry lab, that can only be obtained theoretically. The actual yield is what we are going to work with in the chemistry lab most of the time. This is how much product did we actually recover at the end of our experiment. If that recovery implies multiple filtration, recrystallization, and purification steps, the actual yield is sometimes quite low, but it is always determined from experiment. So if we have a reaction like this, just like for all other stoichiometry problems, we have to focus on the mole ratios. That will drive most of our calculations. Percent yield kind of problems will often provide at least one of our reactant amounts and at least one of our product amounts. That is going to help us nail down which one is the limiting reactant and which product we need to focus on when calculating our theoretical yield. Because the theoretical yield and the actual yield have to be in the same units for the same compound in order for that ratio to eliminate the units and give us a percentage at the end. So when simply reading this problem, we can already tell that there is only one reactant. So that will be our limiting reactant and access reactant in one. And we have 135 grams of sodium carbonate. So that is going to be our actual yield. Let's begin our calculation. If we need to know the percent yield, then the first thing we have to do is determine the theoretical yield from the limiting reactant, which in this case, there's just one reactant. We begin with 150 grams of sodium bicarbonate. In step 1, we're going to convert from grams to moles. Every 1 mole of sodium bicarbonate weighs 84.007 grams of sodium bicarbonate. Then we're going to use the ratio expressed in the chemical equation. For every 2 moles of sodium bicarbonate that is consumed, or in this case decomposed, and we know that because there is a 2 in front of the sodium carbonate, we will have made 1 mole of sodium carbonate. And there is an implied 1 in front of the sodium carbonate in the equation. Because our actual yield is in grams of sodium carbonate, in our final step, we need to convert from moles of sodium carbonate to grams. Every 1 mole of sodium carbonate weighs 105.99 grams of sodium carbonate. And if we complete our calculation, we will have 94.63 grams of sodium carbonate. This is our theoretical yield. This is how much we should have if we successfully decomposed all our sodium bicarbonate. But this is not what we have. Our actual yield is 135.00 grams of sodium carbonate. We divide this by the theoretical yield expressed in grams of sodium carbonate, so 94.63 grams of sodium carbonate. We multiply the ratio by 100%, and we find that we have 143%, which is just impossible. Because if the maximum amount of sodium carbonate that can be produced by the completion of this reaction is 94.63 grams, then 135 grams of sodium carbonate isn't possible. We cannot, through magic, conjure up material in the lab. So how is it still possible that someone could get 135 grams of sodium carbonate? Most likely it is because the heating hasn't been completed and the decomposition is only partially done. So that means that in the 135 grams of sodium carbonate, we don't actually have sodium carbonate, but rather a mixture of sodium carbonate product and sodium bicarbonate that is yet to decompose. Here is another kind of problem. Similar to other calculations, it is a lot more straightforward if our amounts are provided in moles. If we are provided with the starting amounts of two reactants, then in both instances, we need to complete the calculation and determine the amount of product in the recommended unit. So in this case, we have moles of hydrogen. So we will need to focus on that. Let's begin with what we are provided with. 0.25 moles of magnesium. When magnesium reacts with hydrochloric acid, then for each 1 mole of magnesium consumed, it produces 1 mole of hydrogen. So if we consumed all our magnesium, we would be producing 0.25 moles of hydrogen. Similarly, we can make the assumption that all our hydrochloric acid is consumed, 0.34 moles of hydrochloric acid, times, we divide by 2 moles of hydrochloric acid because there is a 2 in front of hydrochloric acid in the equation. And because every time 2 moles of hydrochloric acid react, 1 mole of hydrogen is consumed, we put that on the top. And we find that we have 0.17 moles of hydrogen. Of these two, only one can be our theoretical yield, and it is always the smaller of the two numbers. This 0.17 moles of hydrogen is our theoretical yield. To calculate the percent yield, we're going to take our actual yield from the problem, which is the 0.14 moles of hydrogen, and we're going to divide it by our theoretical yield, which is 0.17 moles of hydrogen. Then we multiply by the 100%, giving us 82.3%. If we have two solutions that are combined to produce an insoluble product that can be separated through filtration, our procedure is the same at first as the one that we used for limiting reactant problems. First, we determine the theoretical yield. We start with the volume converted to liters. For the calcium chloride solution, we have 0.025 liters of the 0.2 molar solution. So for every 1 liter, we have 0.20 moles of calcium chloride. Then we use the mole ratios from the equation. For every 1 mole of calcium chloride consumed, we're producing 1 mole of calcium carbonate in the solid state. And because our actual yield is provided in units of grams of calcium carbonate, then we need to convert our calculated moles of calcium carbonate to grams. Every 1 mole of calcium carbonate weighs 100.1 gram of calcium carbonate, telling us that if we consumed all our calcium chloride solution, we would be producing 0.501 grams of calcium carbonate precipitate. Now we do the calculation the same way with the available sodium carbonate solution. We convert the 35 milliliters into liters. Then we use the molarity as our conversion factor. 1 liter contains 0.15 moles of sodium carbonate. Then we use the mole ratio from the equation. For every 1 mole of sodium carbonate consumed, we will be producing 1 mole of calcium carbonate. And then finally, we need to convert from moles to grams of calcium carbonate. Each 1 mole of calcium carbonate weighs 100.1 grams of calcium carbonate, giving us a total of 0.526 grams of calcium carbonate. Just as every other time, the theoretical yield is the smaller of the two numbers that we calculated in the same unit for the same product. And in our case, that is the 0.501 grams of calcium carbonate. So this is our theoretical yield. To calculate the percent yield, we're going to take our actual yield from the problem that was determined by experiment. 0.40 grams of calcium carbonate. We divide it by the theoretical yield, which is 0.501 grams of calcium carbonate. And then we multiply this ratio by 100%, giving us 79.8% for this reaction. Another kind of reaction that often relies on calculations using percent yield is a synthesis reaction. And here we have copper 2 sulfate reacting with an ammonia solution. Usually it's a concentrated ammonia solution. Usually this experiment begins with taking the copper 2 sulfate, either in the anhydrous or the hydrated form, dissolving it in water, and then adding the ammonia to it. So in this case, the first thing that we're going to do is identify that our problem already gives us all the clues we need to know that the copper 2 sulfate is our limiting reactant. If nothing else, it tells us that we're using an excess ammonia solution. So that clearly says ammonia is our excess reactant, copper 2 sulfate will be the limiting reactant. So it will be enough to just do the calculation using that number to determine the theoretical yield. And then it also talks about the product. We have 2 grams of tetraamine copper 2 sulfate produced. And in this case, we know that our units have to be in grams, and our product that we are watching for is the tetraamine copper 2 sulfate. So let's set this up and go from 2 grams of copper 2 sulfate to estimating, if we used all of it up, how much of the tetraamine copper 2 sulfate could we potentially produce. For this, we're going to begin with the 2 grams of copper 2 sulfate. Then in our first step, we're going to convert from grams to moles. Each 1 mole of copper 2 sulfate weighs 159.61 grams of copper 2 sulfate. Once we are at moles, we will use the ratio identified in the chemical equation. We're going to say, for every 1 mole of copper 2 sulfate consumed, we're going to produce 1 mole of the tetraamine copper 2 sulfate. And then finally, because we are provided with the actual yield in units of grams, we need to convert from moles to grams. Every 1 mole of our tetraamine copper 2 sulfate is going to weigh 245.79 grams. Giving us an estimated amount of product of 3.08 grams of the pentaamine copper 2 sulfate. To calculate the percent yield, we're going to take our actual yield from the problem which is the 2.00 grams of the tetraamine copper 2 sulfate, divided by our theoretical yield, which is the previously calculated 3.08 grams of the tetraamine copper 2 sulfate. We multiply this ratio by 100%. We notice that it's the same grams and the same product, so that cancels out, giving us a yield of 64.9%. And this is a fairly realistic number for making a coordination compound of copper.